Now we're going to jump into the different types of intermolecular forces. We're going to start with London dispersion forces, or LDFs. So LDFs get formed by all particles, all atoms, molecules, everything has LDFs. It is due to the fact that, in an atom there are electrons. So if I have an electron and they're moving around all over the place, there is a possibility that at a given moment that an electron is on one side of the atom, making a very temporary little tiny dipole of negative charge over on that side where the electron is. If another atom happens to be close, or atom or molecule happens to be close to that other particle at that exact time, then the electrons in this other particle are repelled by this electron right here, and so they shift over here, creating a partial negative on this side and a partial positive on this side. So that very quick and temporary deviation of the electron creates this temporary dipole, creating an attractive force between these parts of the atom. And so that's what it is. It's due to the polarizability of the electron cloud, which gets it distorted. Oops. So we look over on our subatomic view, we see atom A. It has one electron that happens to be closer to the right side, causing the electrons in atom B to be forced over to the right, giving it a partial negative over here, partial positive over here, and a partial negative on this side, and a partial positive on this side. And right when those forces happen, then atom A moves away, and atom B has this temporary dipole, and then if it runs into another atom, then it can create a temporary dipole. So if we have nonpolar molecules or atoms, any type of nonpolar particle, this temporary polarizability can create these dispersion forces. So what I want you to know is all particles, atoms, molecules, everything have LDFs. Everything does. So if I ask you what kind of intermolecular forces does a certain atom or compound or whatever have, you're always going to put LDFs. So let's talk about now what impacts LDFs. So first thing is, as you maybe have thought, is going to be the number of electrons. The more electrons you have in there, the more ability for polarizability, which is going to increase the LDFs. So that means if I have an atom of helium, right, helium has 2 electrons in it, versus an atom of argon. Argon is also a noble gas, and it has 18 electrons, which means argon has way more opportunities for its electrons to get polarized to one side or the other, and that causes that temporary dipole. Another thing that impacts it is the size of the atom or the molecule, which kind of gets along with electrons, but the more amount of atoms in it, so more amount of, that just basically means that we have more electrons. So the bigger the size of the atom or the molecule, so if I had like CH4 versus C2H6, methane over here has a smaller molar mass, meaning it's going to have lower LDFs, and ethane over here is going to have a higher molar mass, so it has higher LDFs. So if we look at the size, and that means it's going to have more electrons in it technically, there's going to be more possibility for LDFs. And then the last thing is about shape. So if we look at something like pentane here, we have a long chain of pentane, we call it N-pentane. Both of these molecules have the molecular formula of C5H12. And so if we look at the long linear structure of N-pentane versus neopentane, which looks more like a sphere, they actually have different boiling points, which is really interesting. So what explains this? When we have the spherical molecule, it has a lot less of surface area that can come in contact with another molecule of neopentane. So the amount of contact it gets is low. So low contact means that it's going to have a less likelihood of polarizing other molecules. Over here, this linear molecule has this larger surface area between the molecules, and so they're able to have a higher interaction that allows for the dispersion force to increase. So higher contact or higher long chain equals higher LDFs. So we want to look, the biggest thing is more, like bigger size, whether that's in electrons or molar mass, equals higher LDFs, and long chains equals higher LDFs. So we want to consider both of these factors when we look at a molecule, and keep in mind that as we move forward to the next type of intermolecular force, all of them have LDFs in addition to other types of IMFs that might be occurring. The next type of intermolecular force is dipole-dipole interactions. This happens between polar molecules. They have a permanent dipole. So we have like one side over here that's partially negative, one part over here that's partially positive, right? It's not an ionic compound, so we do have this partial here. But due to that, it doesn't move around. It is part of the molecule. This leads to the opposite charges, opposite ends attracting to each other, and it's more permanently going to do that. It's not going to be moving around as much, and so they're attracting together and kind of staying put. Also, we have positive ends of one side repelling positive ends of the other. So here we see a repulsive force. So we also are balancing both the attractive forces between dipole-dipole interactions and the repulsive forces. So for this one, how it changes, we want to, when we're comparing the dipole-dipole forces, we want the mass and size to be comparable. And this means that the LDFs are going to be about the same. So here we're only looking at the polarity. So the higher the polarity, or the more polar something is, the higher its boiling point is going to be, or the higher the dipole-dipole interactions. So here we have propane, completely nonpolar, a bunch of carbons and hydrogens in there, that's it. And so it's nonpolar, it's going to have a lower boiling point. Now we throw an oxygen in here. Now this oxygen in the middle, it's like balanced on the right and the left, and there is a little bit of polarity on this side. It's more in the middle. So it's still kind of symmetric, and that has a little bit higher of a dipole, and then we see the boiling point does go up from 231 to 248 Kelvin. If we put the oxygen on the end here, now it's making it a lot more asymmetric, and so the dipole unit goes up and our boiling point also gets raised. And then lastly, when we have a nitrogen here on the end and there's no hydrogens on the side to kind of balance it out, we end up getting a much higher dipole moment and our boiling point goes up even more. So main takeaway is increasing polarity or your dipole moment makes the dipole-dipole interaction stronger. So I do want you to consider which is stronger. So we're going to be looking at, you're going to be asked questions, which ones are stronger, dipole-dipole or London dispersion? And really the answer to this question is, it depends. If we look at something like boiling point to determine whether something has the strength of the intermolecular forces, I could look at something like acetone, which has a molecular formula of CH3COCH3. Okay, so we have this oxygen in here, kind of similar to this guy up top, the dimethyl ether. It has a polarity, and we know acetone, it's liquid at room temperature, so it has a boiling point probably somewhere in the 70 degrees Celsius. But we have something like, let's say, oil, vegetable oil. Vegetable oil is very nonpolar. It has a huge molar mass, though. Its chemical formula basically is a triglyceride, which has carbon, 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 with some hydrogens on it, and then we have some oxygens here, and then these long chains, and those wiggles, every single vertex on this is a carbon atom surrounded by hydrogens. So very big molar mass. Now we know that oil is nonpolar because it doesn't mix with water. And so that means that it should only really have LDFs. It has a lot of LDFs. These LDFs, though, are going to outweigh, they're a lot stronger than the dipole-dipole interactions in acetone. And that's because the molar mass is so high and the surface area is so high for these triglycerides that it allows for them to stay at liquid at room temperature and above. Like if you leave acetone out in an open container for, say, a day, it's going to disappear, right? It's all going to evaporate. If you leave oil out for like a year, it's still going to be the same oil. None, like very little, if at all, is going to evaporate because the LDFs are so strong. So which will have a greater effect really is molecule dependent. When the molar masses are very similar, like we have in this case, right, molar mass 44, 46, 44, 41, molar masses are very similar, then now we know we have similar LDFs. But when the LDFs vary and the polarity varies, you're now comparing apples to oranges, and that's going to be a lot more complicated. So you really need to look at the shape, the molar mass, and the polarity, and making sure that the shape and the molar mass are comparable. So you're just comparing polarity to see how the dipole-dipole interactions are going to change. So let's look at this graph. We can see for group 4 elements, so these are all ones that are like carbon and it's all of its group below it bonded with hydrogen. We can see as the molar mass increases, we see that the boiling point or the amount of intermolecular forces increases. And that makes sense because as we increase our molar mass, then that means we're going to increase our IMFs. Right, specifically in this case, it would be LDFs. All right, so now let's look at these other ones. We'll start with group 5. Group 5 is nitrogen's group. So it has this one. Let's look at this trend for the second compound and above. All of them have a lower molar mass with a lower boiling point. We increase the molar mass, we increase the boiling point, and so on. So that makes sense. But we have this weird deviation where it starts up really high and then it drops. And that happens for hydrogen in that group 7 as well as water in group 6. So we can assume that the reason why we have an increase from silicon, the silica compound, to this one above it is because of polarity, right? We have nitrogen. With these other compounds, we have a higher molar mass. We also have a higher, some of these particles are polar. But something weird is happening with this group, the first elements in period 2. So we see that the period 3, 4, and 5 elements, as their molar mass gets higher, their boiling points get higher. But for period 2 elements, after 4A, so after carbon, the trend is a little weird. So let's figure out why. This has to do with the very extreme dipole-dipole interaction experienced when hydrogen is bonded to either nitrogen, oxygen, or fluorine. It's actually really strong. So why is it so strong? If we look at what hydrogen is a single proton, right, and a single electron. I'll put it here. And when it bonds to some of these, well, any element, but when it specifically bonds to, let's say, fluorine, we know that fluorine is very electronegative. So even though it's going to share this electron with it to fulfill its octet and create this covalent bond, fluorine is pulling on the hydrogen's electrons so hard that it basically pulls it almost off. And it creates this like exposed area in the hydrogen atom that's very partially positive. It's almost like the nucleus is exposed. So it creates a huge positive dipole over here on the left towards the hydrogen and a huge negative dipole towards the fluorine. And that's a lot more of a dipole than we had for any of the other atoms, mostly because fluorine is really small. It has a small radius, so it could really get in there really close to the electrons and the nucleus of hydrogen and pull even harder, right? Because if you think about a magnet, if I have a magnet that's separated by a larger distance compared to a smaller distance, this smaller distance, you're going to feel the force of the magnet a lot stronger than when it's far away. So since fluorine is super, super small, right, it's one of the smaller atoms, that, and it's also one of the most electronegative ones, then it's going to get in there really close form this really small chemical bond and pull those electrons almost completely off of the hydrogen. Not so much that it's an ionic compound, but pretty damn close. So we call those interactions here hydrogen bonding. It's the interaction between hydrogen and any other technically small yet highly electronegative atom. So specifically, it's going to be nitrogen, oxygen, and fluorine. So once again, why is it nitrogen, oxygen, and fluorine that does hydrogen bonding with hydrogen? It really has to do with the fact that they are so tiny, right? Very small radius, which when they connect or bond with it, it basically exposes, making the hydrogen a bare hydrogen nucleus, which is basically just one proton, and no other inner electrons to balance it out. So hydrogen ends up being very positively charged, and the other atoms end up being much more negatively charged, and we hit this huge dipole. So really, hydrogen bonding is just an extreme version of dipole-dipole interaction, but it's so strong it gets its own name. I want to be clear that hydrogen bonding is between molecules. So while we need to have, you need to have a hydrogen bonded to an oxygen, nitrogen, or a fluorine, so fluorine, nitrogen, they have to be attached. The hydrogen bond really is between the molecules. So here I have a partially negative side of water, and here's my partially positive side of water, negative and positive. My interaction is going to be between the oxygen on one molecule and the hydrogen on another. So that's the hydrogen bond. This is not the hydrogen bond. Okay, it's not the one in the molecule, it's between molecules. So let's practice. We want to identify which of these substances can do hydrogen bonding. The first thing you need to do is actually look at their chemical formulas. So we're going to need to draw Lewis structures. And it wants to know which of these is most likely to be liquid at room temperature compared to something like gas. So it's basically asking which of these is going to have the highest boiling point, making it a liquid at room temperature. So we would need to draw the formulas here. Let's just draw those out. I'm going to actually let you practice. You could double check online for the formulas, but this is very much something we just practiced in chapter 9. So here are all of the formulas, and they all have the octet. Now I drew them on like kind of more of a grid, an XY coordinate, so we can really review what does it mean to be polar and nonpolar. So we look at this molecule here. It is trigonoplanar. All of the atoms are not the same, so this is a polar molecule. Same thing with the fluoromethane. We have fluorine here and hydrogens are elsewhere, so this molecule will be polar. We have hydrogen cyanide, which also has the terminal atoms are different, making it polar. Here we have hydrogen peroxide, which has these lone pairs on the oxygen, so central atoms, making this molecule also polar. And then we have hydrogen sulfide. Again, the electrons on the sulfur make it a polar molecule. So all of them are polar. So they all have LDS, they all have dipole-dipole, so let's see how they're different. In this molecule, the first molecule that we're going to do, we have carbon bonded to an oxygen. The hydrogens are not bonded to they're only bonded to the carbon. So that is just going to be dipole-dipole. If we look at this next one, we have carbon bonded to the hydrogens, but the carbon is bonded to fluorine. The hydrogens are not bonded to fluorine, so this is also going to be dipole-dipole as the strongest force. Next one also has nitrogen in it, but it does not have a nitrogen bonded to a hydrogen. It's bonded to a carbon, and so this is also going to be dipole-dipole. Now in hydrogen peroxide, we have oxygen bonded to hydrogen in two places. So this is going to have dipole-dipole, but also hydrogen bonding. And then lastly, we have sulfur bonded to hydrogen. Nothing special there. That's also dipole-dipole. So the only one that has the strongest hydrogen bonding intermolecular force is hydrogen peroxide. And we already know this is a liquid at room temperature because you probably have it in a brown bottle in your bathroom. So this other question is very similar. It wants to know which of these molecules has hydrogen bonding. Once again, you're going to need to draw it. So here we're going to draw. We have carbon bonded to some hydrogens and some chlorines. You should practice doing the Lewis structures the right way. This is my shortcut, as I've been doing this for a long time. Phosphine is very similar to ammonia. It looks like this. Chloramines, NH2 bonded to a chlorine. And then acetone, oh, we've talked about that, CH3, COCH3. So we have hydrogens not only bonded to carbon here, so no hydrogen bonding there. Hydrogen bonded to phosphorus, no hydrogen bonding there. Here we have hydrogen bonded to a nitrogen, so yes, there is a hydrogen bonding potential there. And here all of the hydrogens are bonded to carbon, and so no hydrogen bonding with acetone. The last type of intermolecular force, which you won't really see much in this chapter, but you are going to see in chapter 13 on solutions, is the ion-dipole interaction. This happens between, specifically when you have a polar substance and an ionic compound. Usually that polar substance is water. What happens is when we have an ionic compound, so let's look, I'm going to draw something that looks like salt. So we have cations and anions alternating right in our lattice structure, and pretend it's a big chunk, right, in 3D. So then I have something like water. Now water has oxygen and hydrogen. So we have our partially negative side of water and we have our partially positive side of water. So water is going to attach to all of these ions, and a bunch of waters are going to come and like attack them when we mix these, like right, if I put salt into water, they're going to interact on the surface. And so oxygen, the oxygen side is going to go and attach to the cations, and it's going to attach and kind of bump into them hard enough until eventually, if it dissolves, if it is soluble, it's going to pull off the ions and create this cation that is hydrated or surrounded by water. What happens to the anion is the hydrogen parts of the water are going to come and attack it, and it's also going to bump into it enough and attract to it enough that it could, if it's soluble, it'll pull it off. And we get an anion, and we have the water, the hydrogen parts of the water coming and attaching to it. It kind of looks like a cute little sun, and it is hydrated with the water. So that's what ion dipole is. It's a strong enough force to break ionic bonds, cause this lattice structure to break apart and dissolve, and you do that by having this really strong force. So if we look at all of the IMFs, we have dispersion. All molecules and atoms, it's more of a temporary. It can go from a low amount to a fairly high amount if you get really high molar mass. We have dipole-dipole, only happens for polar molecules. It's a permanent dipole. It can be stronger than dispersion, but it also doesn't have to be, it depends. Hydrogen bonding is a special type of dipole-dipole, specifically between hydrogen molecules of hydrogen bonded directly to fluorine, oxygen, or nitrogen. That's even stronger. And then we have ion dipole, which is a mixture of ionic solids and polar compounds, and those are very strong. So let's just review and keep this in mind, that all chemicals are going to have dispersion forces, and the strongest force that the molecule has is going to dictate the type of attractions it's going to do, or how much the attractions are. When we have molecules that have comparable molar masses and shapes, that means that the dispersion factors, or LDFs, are roughly equal. When they have very different molar masses, though, and we don't have hydrogen bonding, then the dispersion forces are going to determine how strong the attraction is. So the higher the molar mass is going to be the higher the attraction. And again, this is not for when there's hydrogen bonding. This is specifically when we're just either dealing with polar molecules or nonpolar molecules. So nonpolar molecules with really big molar masses are going to outweigh the dipole forces of molecules with small molar masses.